He ascended the highest peak of all, which was like a tower of many stories. Before him lay a wide stretch of sea, with islands of the blessed standing out of the water, and long stretches of pleasant land in view. They were peopled with happy souls, some riding on cranes, some on the phoenix, some on the unicorn. Some were sitting on the clouds, some sailing by on the wind. So many and so startling were the things seen that he could never tell the tale of them. This is an excerpt from an early 17th century Korean folktale in which a young man is taken to contemplate the wonders of the world above the clouds. But what can we expect to find now that we have the means and technology to study the atmosphere?
There are many measurements that we're taking in this campaign. There are gases such as water vapor, which are really important. Turns out that the troposphere is very wet. There's a lot of water vapor molecules in the troposphere, and the stratosphere tends to be very dry, very few water vapor molecules in the stratosphere. So we can tell when we're in the stratosphere. We just see the water all of a sudden sharply falls off and we know we're in the stratosphere. Now, ozone, which screens ultraviolet radiation, is exactly the opposite. There's a lot of ozone in the stratosphere and not so much ozone down in the troposphere. So we can use ozone to also tell if we're in the stratosphere or we're in the troposphere. And in fact, the two kind of go hand in hand.
So we're targeting a large suite of trace gases. So our instrument is equipped to measure common species like carbon monoxide, which is a tracer, which is a marker of the surface air, and ozone, which is also associated with the active chemistry.
Now we also measure other things. Carbon dioxide, nitrous oxide, methane. All of these are important climate gases. On top of that, we measure all of these substances that can lead to ozone depletion.
During the ACCLIP campaign, a range of 50 to 60 different types of gases will be measured, as well as the composition of aerosol particles transported into the atmosphere by the Asian summer monsoon.
Now, why make these measurements in particular? Well, we're looking at issues like ozone depletion. There are man-made gases that can deplete the ozone layer. This is a critical gas for screening ultraviolet radiation. So we want to know what's going to happen to the ozone layer. Are there certain man-made gases that will accelerate ozone depletion? Are we seeing gases that have been controlled by international treaties? Are they falling off?
Chemical compounds transported into the stratosphere can have a major impact on the climate system. Many of them can be tracked by ground stations and are well known to the scientific community and the public because of the negative effects they can have on the ozone layer. They are called the Montreal Protocol controlled gases.
So for the, we call them the Montreal Protocol control gases. Those, we're not too much worried about those because we know we can learn about the emission of those gases from the ground-based network. But some of the non-controlled species, we call them very short-lived halogen compounds. We have seen an increased abundance of these gases. In particular, this one compound we really care about is called dichloromethane.
Well, we use dichloromethane for a number of purposes. It can be used as a solvent for cleaning things, for example. And this gas has chlorine in it, and chlorine can deplete the ozone layer. So the levels of dichloromethane have been going up. Down here at the surface, we have measurements from stations. They tell us dichloromethane is increasing.
Compared to the very long-lived CFCs, everything gets into the stratosphere. However, with dichloromethane, because it's relatively short-lived, a fraction of it gets into the stratosphere. So we also want to know, using ACCLIP measurements, what the fraction is.
That's a key question to understand ozone depletion. Knowing the levels of these man-made gases, how much is getting from the surface down here, we have ground measurements down here, but how much gets into the upper atmosphere, into the upper troposphere, and into the stratosphere, where it can cause ozone depletion.
So we need to track not only the concentrations of these gases, but also their lifetimes to understand their impact on the atmosphere.
We also want to take a look at climate change and how are gases affecting climate. Many of these gases have tremendous climate impacts. Carbon dioxide being, of course, a primary gas that's produced when we burn things. So you get carbon dioxide comes off of burning things. And we can make measurements of that to understand how we're impacting the Earth's surface weather and temperature.
To complicate matters further, it is not only gases and aerosol particles that can determine the warming or cooling effect on the Earth's surface, but also a particular type of cloud.
Cirrus clouds are very unique. They're the most abundant cloud on Earth, but they're also the only type of cloud that can both absorb and reflect radiation. So they have a warming and cooling effect depending on the conditions. The thing is, though, that the overall radiative component, so the role they play in the climate system, is not well constrained. And so by doing these measurements, we can put better bounds on the impact of cirrus clouds in the climate system. And so the NASA WV57 allows us to get to 50, 60,000 feet. So here we can make direct measurements and get a sense of how large or small the cloud particles are and just how much of a radiative effect those really thin clouds have, because they're everywhere. They're covering large swaths of the globe.
So in addition to the two research aircraft, we also have a team launch the balloon sound from the ground. This balloon sound will cover a large vertical range all the way to 25 kilometers. So that covers the entire layer, starting from the boundary layer where the emissions happen all the way to the stratosphere. And that helped the aircraft calibrate the vertical range of this layer and where the aircraft data will fit in. So it's a three-dimensional process. Yeah.
So, as you can see, trying to better understand our atmosphere is a complex issue that requires measuring, working together, and collecting huge amounts of data.
So, airborne science missions like ACCLIP have a primary goal of improving our understanding of sort of fundamental aspects of the atmosphere and climate system. We make the measurements so that we can better understand the climate system, so that we can make better predictions of the climate system going forward. Climate change is and will be a critical issue, and how we respond to that requires information. And missions like ACCLIP and others similar that allow us to improve our understanding of the climate system provide that information so that we can have better climate models and rely on those to then make policy decisions, because we have a better idea of what the implications of various policy choices are.